All right, let's go ahead and take a couple of examples of implicit differentiation. Now remember, all of our rules still apply, so you have to be very careful. But now we have this embedded chain rule here that we are assuming y is a function of x. Okay, so in this first one, we're going to go ahead and take the derivative of everything across. And so if we look at the derivative with respect to x, we get 2x. Now x squared with respect to x, that's all we get. X is a function of itself, and so we don't have to worry about it. But now we have plus 2y. Now y is a function of x, but it's not explicitly stated. And so we need to use the chain rule on this. And so that becomes the derivative of y. So we take the derivative of the outside times the derivative of the inside. Okay. And we don't know what y is as far as y equals some function of x, and so we just say it's the derivative. And the derivative of 36 is 0. So going back through and solving, we have y prime is equal to, we bring our 2x across, so it becomes negative 2x divided by 2y, and that gives us negative x over y. Okay, and that's all the farther we necessarily have to go. It didn't tell us to do anything other than just simply take the derivative, because that's all we're practicing on at this particular moment in time. Now, since you have a y here, you in fact have two different derivatives. This is a circle, and it depends on where you are on the circle, because you can have two different y values for the same x value, and so you notice that it kind of depends on x and y where you're sitting on the circle, and so your derivative can change. Okay, let's go ahead and take a look at another one here. And this one's maybe slightly more complicated. We're just going to incorporate the product rule here in the center term. Okay, so we have take the derivative with respect to x. And now the derivative with respect to x of x cubed is 3x squared. And now if you really wanted to run this, this is the derivative of x times the derivative of what's inside, which is the derivative of x with respect to x, which is just 1. So that doesn't really change anything. However, on the next one, we have the product rule. And so we want to be very careful here. We want to put in our parentheses. Whatever we get, that's what we have to subtract off. All right, so we take the derivative of the first times the second, which is just 1y, plus the derivative of the second, which is y prime, times the first, which is x, okay, plus 2y, y prime, the chain rule. Take the derivative of the outside, derivative of y squared on the outside is just 2y, times the derivative of what's inside, and the derivative of what's inside is the derivative of y, which is nothing more than y prime. All of that equals 0. Okay, so now we'll go ahead and expand it. And we have 3x squared minus y prime x plus 2y y prime is equal to 0. All right, so now here's what I'm going to do. I know I can see here that I have, in fact, some issues because I have a y prime there and I have a y prime there. If you got two things that you want in two different terms, factor. Okay, so we're going to go ahead and move this stuff in green. We're going to move that over to the other side to kind of give us some room. And so I've got, and I'm going to rewrite this slightly, 2y y prime minus x y prime is equal to negative 3x squared plus y. And now I can factor. So after I factor y prime, now I've got y prime times 2y minus x times that whole quantity is equal to, and I'm going to put this stuff in parentheses just to keep it separated when we do the next step, which is divide. Dividing both sides by 2y minus x. 2y minus x. Okay, this is y prime is equal to, all that stuff goes away, negative 3x squared plus y all over 2y minus x. there is our derivative. Okay, so it's not really that bad. You just got to pay attention to what's going on. And don't forget, if you have to incorporate any of these rules inside of other rules, put them in parentheses. We had our sum and difference rule here, but inside of that sum and difference rule, we had a product rule. We have to include that inside the parentheses so that we're distributing our negatives correctly. All right, so now that we've found those two, let's go ahead and move on to the third, which incorporates everybody's favorites. Yeah. Many of the students that I talk to just absolutely loathe doing trig inside of derivatives and integrals, and quite frankly, I love it. I don't know why, but it's just, yeah, it's just really cool. So here we are. We're going to take the derivative of all that stuff with respect to y. Oh, I'm sorry, with respect to x. Silly me. Okay, so we're taking the derivative with respect to x of all that stuff. Start slow. The derivative with respect to x of sine of x is cosine of x equals. That's it. That's all it is. Now we have to run a product rule because here's one spot, here's the other spot. Okay, so we're going to take the derivative of the first, which is 1, times the second, which is 1 plus tangent y, okay, plus, the other plus, the derivative of the second. The derivative of 1 is 0. The derivative of tangent is secant squared. So we have secant squared y times the derivative of what's inside, which is y prime, all times x, the first thing. Okay, so just take it slow and then break it down. So we have the cosine of x is equal to 1 plus tangent y plus secant squared y times y prime x. Okay, so now let's go ahead and see if we can't do something here. Oh, let's take a look at this. It's not going to be very nice, I suppose, but we can get a look at it. Secant square, this is 1 plus tangent. Oh, yeah. Okay, let's go ahead and employ a couple things. So kind of over here in some scratch paper. And yeah, I know I took some time out to think about it, but I kind of wanted you guys to get a feel for, hey, sometimes he has a hiccup too. And so I don't know my identities very well. You'll have to forgive me. But I do know that cosine squared x plus sine squared x is equal to 1. And I'm looking for something for secant, and so I want something 1 over cosine squared. So this is going to give me, if I divide the whole mess by cosine squared x, I'm going to get 1 plus sine over cosine is tangent, so I'll get tangent squared x is equal to 1 over cosine squared, which is secant squared x. Okay, so now when I do this, I can take the cosine of x is equal to 1 plus tangent y plus, and now if I see a secant, I can put 1 plus tangent, or 1 plus tangent squared. So 1 plus tangent squared y times y prime x. Okay, so now I can work this a little nicer here. So I'm going to subtract all this stuff over. So I get cosine of x minus 2, that takes care of my ones, minus tangent y minus tangent squared y is equal to, brain fart, brain fart. Whoa. We can move that stuff, but we can't move the tangent y. We can't move this stuff because we've got multiplication happening, so equals tangent squared y prime x. And so now we'll go ahead and capture all that stuff. And so as we're moving it around, we got cosine x minus tangent y minus 2 all over, divided by tangent squared y x. X tangent squared y. Okay, so that takes care of the x and the tangent squared y. val equals y prime. So that's certainly one answer. Whoop. Certainly one answer that we can come up with. Now I hit this spot, and the first thing I start looking at again is there anything that I can do any more? Do I see any other trig identities out there that I recognize? And I've got this tangent squared, I've got a tangent there. I might be able to do something because I've got a cosine here, except that the cosine is in x and the tangent is in y. Now I suppose that I could probably do something like, well, if y is a function of x, then it's probably arctangent. I don't think it's really going to help my cause any. And so I'm just going to go ahead and I'm going to leave it like this. And I'm going to call her done. Okay. And now the beautiful thing about calculus, and one of its most irritating aspects as a student, is that it guarantees you a unique answer for this. The part that really is not cool is it doesn't tell you what that answer is going to look like. And because of there's so many of those identities out there, what you may get for an answer might look entirely different than, say, what a professor might write down as a supposed answer to a test. And the problem is that you're both right. Because the professor may have put a different trig identity in there, one you weren't familiar with, or one you didn't think of, or that sort of thing, or you might have done the same thing. I mean, so it can get kind of hairy that way. But trust yourself in this. If there's something, for example, if you're doing a problem out of a book and you don't get the same answer as the book, start looking for trig identities, because that's probably what it's going to be.